before I open the floor for questions, if someone is so shocked that needs to go straight for lunch, please go. Because I'm pretty sure that there are many questions. So thank you very much, Professor Ghattas. Really appreciate it. It's impressive. A hand on the back, please. David.
Hi there. I just happened to have worked on a couple of libraries regarding the National Seismic Hazard Model in New Zealand. So I was wondering, with the approach that you're taking here, how much of it is tuned around the specific characteristics of the Cascadia model, and how much we would need to retune it in order to deal with our interesting fault systems over here.
Yeah, so really what we need are just two things: bathymetry, which I don't know how well characterized. I mean, this is 200 meter resolution. This is from the GEPCO data set, and I don't know what kind of resolution you have for the bathymetry along the subduction zone here. So that's one input we need. And the beauty of focusing on the seafloor motion, you could ask, and actually other people who are trying to do this problem also, they're trying to invert for the slip on the fault. The problem with inverting for the slip on the fault is you have to know the fault location, you have to know the fault geometry, and you have to know the wave speed, the Earth model in the solid Earth beneath the ocean. And there's large uncertainty in both of those. And here we subsume that away. We say, no, all right, so there was a rupture, there was slip, it propagated, and it moved the seafloor. What we care about is the net effect. How did the seafloor move? Yes, it's a higher dimensional inverse problem, because it's spatiotemporal. But in a sense, so is rupture on the fault, slip on the fault, if you're trying to invert for that. So by sweeping under the rug everything that happens in the solid Earth, we essentially we don't need much information. We just need the bathymetry, and then to test the system, we need plausible earthquakes. And so that might test the sensor system. Of course, it would also, you'd have to have sensors. But there's with continuous, with active fiber sensing, that some of the dark fiber that's laid out around the oceans is now being repurposed into acoustic monitoring, where if there are any any motion will create backscatter in light waves, and people are constructing these, essentially repurposing these cables to serve as acoustic sensors, but now they're distributed. And so that can bring in a lot of information too. And I don't know what the cable situation around New Zealand is. To go back to Australia, and then I don't know if there's anything to the east of the country. But yeah, so not much, basically.
Any other question? Or yes, Colton here, or we are just waiting for the tsunami to hit.
That was really fascinating. Thank you. So just a few months ago.
Microphone closer.
Oh yes, thanks for the reminder. Just a few months ago, I was in Japan and spent some time seeing some of Fukushima. I went to the Miyagi Tsunami Memorial Museum, and I feel that Japan has taken that, learned a lot of lessons, and applied them. And I kind of fear that in New Zealand, we don't have that history, we don't have that record of those tsunamis. And likewise, seeing this is great for what it covers, but I feel we potentially have some gaps here in New Zealand. And what I'm wondering is, with this information, the simulation, seeing where the waves will go, how you anticipate people will ingest that information, what differences it will make in the early warning system, opposed to there might be some conventional knowledge is long and strong, get gone sort of thing. And if there's an earthquake, there will be really early warning. There might be a tsunami, get to high ground. And I wonder what sort of differences, tangible differences, you see in the warning system with this.
Yeah, all excellent questions. I spent a little bit of time digging around some of the government websites, and there are animations. I actually don't have any here, but that show various earthquakes and potential seismic wave propagation as well as tsunami propagation, and those are meant to inform the public. And so, there seems to be a very active effort. But you're right, there isn't the long period of recorded history. It was in Japan, there was that recorded history of tsunamis, and they used that to inform. Unfortunately, in Fukushima, the northern part of the island and the southern part, the protection was at a higher level than the central part where Fukushima was, because it was thought that the plate was not active, that the subduction zone was locked off of Fukushima, and the probability of rupture there. Actually, they hadn't seen in 1,000 years of recorded history. There was no record of a rupture. So I think it was 10 meter seawalls that are protected against 10 meter tsunamis. Where the other parts of the country it was 20 meters, and then the 2011 event hit, and that reached 20 meters and above. And so if they'd had that kind of protection, that could have avoided. So yeah, Japan is the best prepared country in the planet, and they've got seafloor pressure sensors. Not many. They have a handful, but I think they're in the process of deploying more. That most of the damage in that 2011 earthquake was the tsunami generated. The actual buildings held up fine because their building standards are high. Actually, I learned that New Zealand has very strict seismic standards on buildings, and the damage that occurred in Christchurch was just because of this unexpected earthquake location, because buildings might have been weakened from the 2010 event, because there was significant liquefaction, as the strong waves sort of caused the soil particles to separate because of the pore pressure, and then the soil would just liquefy, and then once that happens, nothing will withstand that. But I think there's a high level of awareness here. What a tool like this can do is, seismologists need to define earthquakes on a fault system. Let's say 1,000 potential earthquakes on the subduction zone, and then we can build priors and then solve the inverse problem with these priors and say, look, and select one that wasn't part of the prior set. Select that as a test, and select a handful of test earthquakes and say, how good is our predictive capability? And then use that to inform the design of an early warning system of these pressure sensors. So that's where a tool like this would be useful.
Couple of comments regarding Christchurch earthquake. My daughter was in the earthquake. I live 3 hours south. There were 185 deaths, on 110 in a single building, which was, they just tweaked the standards. It was poorly designed, and it was a language school there, and then the building flat down, and 110 people died on that specific part. So.
Was that an old building that was built before?
It was in the 70s, but someone just signed and didn't read, or someone, human thing, right? Yeah. So, but I stand to be corrected, but the same magnitude of earthquake that happened in Christchurch happened in Haiti and Port-au-Prince and had 300,000 deaths.
Exactly.
So that's one thing. Other comment is you probably refer to the simulation which is in YouTube about the Great Fault, the Alpine Fault, which is here, which starts here and then starts to propagate and moves in some way. I luckily live here, so it was true, but that's a personal comment. It wasn't.
So you live around there?
Yes.
Okay.
So, but the point is that this animation was, again, made at the University of Canterbury 10 years ago, hasn't been touched or updated since, which brings me to a question from a managerial point of view and thinking on my children. Because, you can give me a round figure about how much time, investment, effort, we know how to calculate the computing, and still you are preparing for a problem which is 20, 40 times smaller than what actually be. If I am facing a government official which say, look, I have a few $1 billion to predict something that could happen or not in 100 or 200 years, and I am short-sighted and I am just living in the times that we are living, I will say, well, maybe I do something else. And that's an open question. That's, I do multicultural just to do these sort of questions. Is that something that you have been facing? Because I was listening to your fantastic presentation and I thought, okay, that's why 40 years ago I was teaching calculus. That's why, I can follow some of this, but at least I wonder how many 15 to 25 years old realize what an eigenvalue is at the very beginning, right? So on and so forth. So are you facing these reality checks in front of government officials or someone who is actually funding? So if you want to continue this work, Dan can tell you, okay, this is how many hours, this is that and that. So think on long terms, because you say, okay, we are saving trillions, but which is the probability? So why don't I just face destiny and we go down? And before that, we just enjoy life. I'm being stupid on purpose, and I'm not saying that government officials, no.
But it could be the opposite. You know what happened in Italy with the seismologists who, there have been some pre-shocks in a region in central Italy, and there was some seismic activity, and a group was brought in. They're asked to assess the situation, and their technical report was very accurate and said, look, there is a probability there could be a magnitude 6-ish earthquake in the coming months. These could be just pre-shocks for leading up to a main event. But then when the head of the group came out and gave a press conference, he sort of hid the uncertainty and the feeling of the committee that, maybe there is some kind of probability, it's low. And he just said, no, everyone's fine, just go home and have a glass of wine. And anyway, earthquake hits, what was it? Does anyone know? A week later, 2 weeks later, a month later, magnitude 6-ish, killed hundreds, caused a lot of destruction. And he was arrested. And there's a group of geophysicists were arrested and put in prison, and because they failed to predict an earthquake. We can't predict earthquakes. And they were tried, and now there's a huge international scientific outroar, and eventually they were released, but they were still, convicted of failure to predict an earthquake. So I think we need tools like this. So this is not predicting when an earthquake is going to happen. It predicts if an earthquake happens, these are the consequences. In the tsunami case, we have 20 minutes to the nearest town that will be inundated, and so I think we can give early warning. That's enough time to seek higher ground. We can do the same problem, but invert for the fault rupture. As I was saying earlier, that we don't do that, but we could actually do that by coupling in the seismic waves with the acoustic waves. And then once you have the fault rupture, forward predicting the solid earth waves, so the shaking on land, you can also do that. Now there you don't have much, you have maybe 30 seconds, 45 seconds. The seismic waves move much faster than the acoustic waves. So we could do that, but it wouldn't be to give people 30 seconds isn't enough warning. Maybe you get under a table or something, but it's enough. It's for early responders. It's for saying these are the ground shaking accelerations. Send people there. These are the maximum ones. And these two kinds of tools can be built. And this is one research scientist, one graduate student. The last person listed helped out with some of the GPU optimizations. And then Alice just came on recently to bring in some of the earthquake prior knowledge. It doesn't take a lot. And I think we just need to keep doing basic research and making the case.
Join me thanking Professor Ghattas for the fantastic talk.
Thank you.